Thank you for joining us today. The topic of today's webinar is distributed stack tracing and monitoring for serverless applications. When you're running a large fleet of serverless applications, how can you efficiently diagnose performance issues? In this webinar, we will look into some of the aspects of debugging and diagnosing your serverless application. We will also show a demo of AWS X-Ray. It's a distributed stack tracing service, and how you can use that to efficiently diagnose performance issues and monitor your serverless application. Let's get started. I want to start off with Amazon's story towards building a distributed application. During 2001, or prior to 2001, we had this Amazon application, which is a monolithic application. There are several application teams and different components that what made Amazon.com. And all that is getting deployed and built in a single stack. So we had this transformation back in 2001. So post 2001, we started demonolithing our application into several microservices. And these are independently operated microservices. They connect to other microservices. And what we call them internally as two pizza teams, which essentially means you can't feed a team with two large pizzas, then either they have a big appetite, or more to the point, your team is too large. So it's a methodology we use internally where smaller teams can operate a little bit more efficiently and control their microservices and their release cycles. So event-driven computing maps really well with microservices. When you look at a typical event-driven application, there are various endpoints for various functionalities, and each of them get invoked can invoke different microservices on the back end. So microservices from a monolith to a microservice model using event-based computing works really well with the serverless applications and microservices. As part of the next iteration, event-driven computing also maps really well with functions as service. In a typical serverless application, your function is really the core unit of compilation. So in that case, every single event is mapped to a specific function on the back end. In a typical serverless application, AWS Lambda is at the core. AWS Lambda is our fully managed, highly scalable function as service. So in this particular case, we support several languages, several variants of Node.js and Python, different versions, and Java and C#. Typically, there's an event source trigger, which can be a change in data or resource state or incoming request. Lambda can trigger that event and save the state into a persistent data store like DynamoDB, or it could be calling another service, or it could be calling another Lambda function. So now that we have defined a serverless application, let's take a look into stack tracing. In a traditional environment, the common school of thought is, okay, let's go ahead and install some agents and set some breakpoints and debug the trace. But that doesn't really work in a serverless application. So let's start with comparing the differences between a traditional host-based application and a serverless application. In a traditional application, typically there are agents in the host monitoring and sending data. It can be a challenge to separate the signal to noise ratio of an actual application component to the whole. On the other hand, in a serverless application, the infrastructure resources are not persistent. They come and go on demand. We only get data when there's an actual execution is performed. It is easier to distinguish an event from various services. For example, event A versus event B or C, you can distinguish them based upon the data that you have if it is a serverless application. And also, as with any AWS services, you're not paying for idle time. You're in the pay-as-you-go model, and you are paying for the resources that you're using. If you look at the serverless compute manifesto that we released during re:Invent last year, it primarily focused on function execution as a unit of deployment and scale, where you're taking advantage of on-demand compute and not worrying about the scale or state management. You can bring your own code, develop your own services. What it essentially means is if you have libraries that you're sharing across your teams, across your other parts of the organization, you can package it up into an artifact, and you can deploy that in Lambda. And you can do in any of the supported languages: Node.js, Python, C#, and Java. Let's look into the metric and logging component of the serverless compute manifesto in this part. To understand what's going on in your application, traditionally, it's done with logs to identify any problems with your application. Let's take a look at what options we have available. Amazon CloudWatch is an AWS managed service, which can be used to monitor AWS services. You can collect and track metrics, monitor files, and automatically react to changes in your AWS resources. Specific to Lambda, there are 6 built-in metrics, and there's support for custom metrics as well. Also, there are 7 built-in metrics for AWS Amazon API Gateway. You can use this to identify a number of times it got invoked, error code count, latency, and other pertinent information. If you navigate in the console, there are other dashboards that are ready-made that is available for you to see all these metrics. So there is several support for CloudWatch logs. There's a distinction for logs for error and info, so that way you can actually focus on the error information. And optionally, you can get the log method request or body content as well. And Lambda-specific logging, you can do console.log and add a lot of logging information that can be available using CloudWatch logs. So when you're executing a Lambda function, you can have CloudWatch logs show all your log information as it executes your code. You can also build metrics and export logs to AWS Elasticache or S3, and then explore that using Kibana or Athena or QuickStack. We have several blogs that discuss this workflow as well. So these are some of the common patterns. But what happens when you have a 2-tier or a 3-tier application? So you have API gateway in the front, and your business logic layer is your AWS Lambda, and your persistent data store, in this case, is the DynamoDB database. It's fairly trivial to diagnose logs and to make a sense of a function call that is coming to AWS Amazon API Gateway, to Lambda and DynamoDB. You can set thresholds and dial up or down the number of logs you're getting recorded to get more data around specific function calls. So you can correlate all these logs in a fairly straightforward manner. But what happens when your Lambda function requests a callback to another service which links to an Amazon API Gateway endpoint? And what happens when your Amazon API Gateway endpoint connects to another Lambda function that points to another notification service using Amazon SNS or using DynamoDB? So there's a lot of calls to obviously manage, and it can be tedious and complex to understand where these logs and how they correlate with each other. All of a sudden, the landscape becomes significantly more complex. So if you were to correlate the logs between your databases and multiple Lambda functions, and if you were to build a solution around looking at logs or timestamps you're probably thinking about a solution that you have to build it on your own to correlate different timestamps with a correlation ID, which can be programmatically put into logs. At this point, you're probably building a tool to help solve a very complex solution for your distributed application. So what options do we have at this point? You can't install a traditional APM solution. You can build a tool that correlates all the logs at the application level and sign up for perpetual ownership. And in a lot of times where this process could be tedious, and you're building and spending your cycles really maintaining the solution for perpetuity. Or we could use AWS X-Ray. AWS X-Ray helps you debug and analyze your microservice application. It traces the request made to your application. It collects and records the data about the request. You can view your service map to see the trace data and analyze issues. So typically there's a request that is getting made, and you trace that request, and you record the trace, and you analyze the issues. This is what a typical AWS X-Ray trace looks like, and it is in a JSON format. That is a representation of the request that your application serves. Don't worry about parsing this. Let's break this into different segments. The segment records the trace ID, name and start time and end time of the request, the information about a request and the response. In this case, the state is the number indicating the HTTP status of the response. And the resource is the resource ARN. Some of the concepts before we get into AWS X-Ray, a trace is related to a single request across services. Inside that, there are segments and subsegments, which correspond to a single service. Segments and subsegments can include annotations. These are basically filters. So when you have to query your trace logs, and you can use different filters to basically query these pertinent information based upon your filters. Metadata is the additional data that can be added to the trace to provide more context that can come in handy during debug time. Like, for example, a specific application call inside a function that you want to call, you can add that in the metadata field. You have information about traces, and you can get metrics on how much your application requests are traced. And these are provided, the sampling information is provided out of the box. So service map gives you an overview of what are the different services and which service is calling which and what are the dependencies. If you remember in the traditional environment, understanding the dependency matrix of an application can be really challenging, and it's really a lot of work to put together. So in this case, you can go to the service map tab and see all your services and how they're getting linked to each other. And the green color indicates everything is working fine in that service. Trace segments can be used to view downstream calls made from your Lambda function. So in this particular case, the Lambda function can call other functions. In that case, you have those information separated. The time taken to execute and average latency are available in that service map screen as well. This includes the failure rates as well. So the orange indicator here tells you there is an error in my function. It says there is an error state. So let's take a look at the exception tab and see what is the failure. And in the trace, you can see what has failed. So you have the stack trace information, that maps to your specific function call with the line number. So what tools that are available for you to build applications or use AWS X-Ray with your Lambda functions? AWS Lambda provides basic instrumentation support for all runtimes. You can instrument your Lambda functions with the same methods that you use to instrument applications running on other services. Currently, we have support for Java, SDK, Node.js, and we just released a Python beta support. And you have some capabilities to add filters to automatically capture metadata for those calls. And these are this SDK is available for you to get started quickly without having to instrument your application code. There's only 2 lines of code to enable tracing. In the first 2 lines, you would see initialize the AWS X-Ray SDK core, and you're starting capture. So all the calls that are made after that are fully traced in X-Ray. As you make changes or add new functions, you will see the service map overview kind of changes. And then function changes are reflected in real time. As the Lambda functions get executed, you will see the status of those Lambda functions added to the service map. And we also provide a waterfall view of your function execution workflow. The green checks, those are specific calls made inside that Lambda function, indicate that the function seems to be operating as expected. We also provide a set of APIs, so you can send trace data directly to the service without having to use our SDKs. There are 4 different API calls where you can upload, retrieve list of traces, or retrieve a document, or retrieve IDs and metadata for traces. Although we have support for Python SDK now, Rackspace is an awesome partner of ours, has built an open source tool called Fleece. This includes several wrappers to help report performance metrics to X-Ray. So it automatically wraps all the Boto3, which is the Python AWS SDK calls, and annotate metrics and help the X-Ray console visualizations. And also it wraps the HTTP requests made through request library, and it also has support for decorator that can be applied to any function or method. There are a few things we are currently working on. This includes API gateway support, which presents information about requests that come through it. We currently support a couple of databases. Obviously, we want to integrate with other databases as well. We're currently working on adding support for step function and C# SDK. One more thing to highlight here. This is not an APM replacement. We had several customers ask whether this is a replacement for New Relic or other APM solution. The answer is not. AWS X-Ray does not offer the same capabilities as your APM solution. There's no trend analysis, and New Relic can technically consume the X-Ray trace information. Let's go right to demo. This is a RESTful Java API that uses Spring Framework. Basically, it's an online game for tic-tac-toe. It's created using Elastic Beanstalk. Let me refresh the page. I'm going to go ahead and create a new game. So now let's go ahead and look at the traces for this game. This is the AWS X-Ray console. In the service map, you could see where the clients are getting connected to which API, the Elastic Beanstalk environment, and various forks of this microservice calls and the entire dependency. You can refresh the data up to a few minutes to hours. So based upon the function call that we just made, this is the overview it's providing us. And you can go to the trace tab to get pertinent information for that specific trace. When you go to the trace details, you can see the function calls and the trace list. And inside that, you can see various calls where I'm invoking SNS, DynamoDB, and so forth. You can drill down into DynamoDB and see all the various function calls that are made. Same thing with SNS. So what I have created is the Elastic Beanstalk environment. So I have an environment that I provision. I did upload and deploy code. This sample, we have it available in our documentation. And in my software configuration, I can pass this runtime variables for this environment. For example, notification email. If I want to send a notification, I can provide that information here. So if you want to drill into specific information, so you can click on that, and you have more details available for that particular Lambda execution. You can see the latency information. And on a high level, you can see the error counts and the fault and throttle information. When you go into specific traces, you can group by status code. If you're interested on a specific HTTP status code, you can drill into that information as well. And a method or a specific user, if you have it configured, the user agent, or the IP. So let's refresh the page and let's play another game and see some more data. So in this case, you get a snapshot view of how many responses are okay and how many are throttled and errors. So that can be particularly useful as you are debugging a suite of applications. And you can see the compute map change at real time. If there's a latency on a specific call, I can drill into those specific API calls. So what I'm going to do next is change the variables. And hopefully this would trigger a failure. So what I'm doing is triggering a new deployment in Elastic Beanstalk with the updated parameters. And this screen will tell me once the deployment is completed and the dashboard where it turns healthy. So here, I have provided an incorrect email ID, so there's a fault. So you can drill down to this fault. And this is the exception tab, where you can see specific stack trace for that function call, and it tells you invalid email address. And these information is right at your fingertips, where if you added any metadata about your function calls, you can actually see them here, any annotations that's available. And this is your parent ID and a subsegment ID. So let's go ahead and fix this. For that, I'm going to go to the configuration. Currently, there's a deployment process. Let's wait for that deployment and see if we can update that change. And other neat information that you have available, if you want to really look into the actual payload, you can go to the raw data and see the specific documents and the HTTP request to the actual URL and the payload information, and then the service origin, and etc. So let's see if our deployment completed. Okay, successfully completed. Let's trigger a new game. So I'm refreshing the service map to see what other changes that I have available. So in this particular case, I'm going to go ahead and update the environment variables. So hopefully the error that we saw will go away. You can use the events tab to see monitoring information of your new deployment. So once that is the case, once the deployment is completed, then we will go revisit this and see if this error has been fixed or not. Okay, let's go back to the slide deck. So what we have is a serverless, there's a serverless computing landing zone. So let's take a look at that. So you can simply search for AWS Serverless, and this is our landing page. We have a lot of information specific to AWS Lambda, getting started resources. We have specific use cases where you can apply for real-time streaming, data processing, mobile backend, and web application. These are references to architecture that's available as well, and also with sample code. And you can just follow along these instructions to learn more about serverless applications and how you can integrate that with X-Ray. And also have some developer tools with links to our SDKs. We also have some information about partner solutions. And AWS Serverless Application Model is how you can define your serverless application that is supported inside a CloudFormation code. And it's a simplified way of defining your various components of your serverless application. Typically, your serverless application, it's not just Lambda function. They are a combination of API gateway, several Lambda functions, and DynamoDB, etc. So all that can be packaged in a serverless application model definition. So you can learn more about that here. And also, we have several third-party frameworks. So I would definitely recommend checking out these because there are lots of libraries that are available to help you build your serverless applications. And we have a couple of blog posts on how to do CI/CD for your serverless application. And also, there's some information about how you can use CodeStar and Code Pipeline and AWS Code Build. Okay, going back to the slide deck. Let's check if our deployment succeeded or not. Environment update completed. Let's refresh the game and see if we see that error or not. So here I'm trying to invoke the trace. Let's take a look at the service map. Usually that's the common way where you can see. If it's all green, then there's probably not a lot of issues. And then once you can drill down into the traces, now you see that information about SNS topic. It's successful now. There's no faults. So hopefully that gives an idea about how you build your serverless application and deploy it using Elastic Beanstalk, and also specifically debug your application, including looking at the stack trace using X-Ray. And that's all I have for the session. If you have further questions, we are available on the chat window, and feel free to ask some more questions, and or send me an email at balaiyer@amazon.com.